I have this and then like a bunch of downstairs, pathogenic microbiome, micro this and then calculus. So we don't. I decided to get it over with. But
okay, so we have, do we have? Ha. Okay, so it looks like we have recording going on. Okay, it's a little bit slow. Not it. We have audio. Everybody's what, 8 people online, and you guys hear well, and hopefully you see the board. Hopefully. And so hopefully everybody sees very well on the back benches over there. At least that's what it looks like. And I see mostly familiar faces, but I'm sure that there are some people that didn't have the first semester with me. At least some people online are in this situation. How many people here didn't have the first semester with me? Okay, so we have 2, 3, and several people online. So let me again go quickly over the rules of the game. Pretty much everything the same like last semester, the same textbook. Catnell and Johnson, 10th edition. However, any other edition, old edition of Catnell and Johnson is perfectly fine. And e-version of the textbook is available together with subscription for WebAssign. So you don't need to spend $200 to buy a paper copy of the textbook. You can just sign for WebAssign, and you're going to have access to electronic version of the textbook. So how to sign for WebAssign, let me see. I sent an email this morning to everybody, but some people didn't receive the email. So if you are registered for the class, or you're planning to register for the class and didn't receive an email from me, please send me an email so I can add you to the email list and you to receive the information that is needed. So let me go over this WebAssign story quickly. The syllabus is pretty much the same like the first semester. The differences are that we're instead of covering 17 chapters, we have something like 14 chapters only this semester. So hopefully the pace is going to be a little bit more reasonable, but it is still going to be very fast paced for people that haven't had physics. So you still have to stay on top of the material. So the material where practically most of the time, the first 7, 8 weeks is electricity and magnetism, which is a very abstract material because humans are not sensitive to electric and magnetic fields. So we're going to talk about topics that are completely abstract. And on top of that, those different topics, abstract topics, are going to sound pretty much the same, like electric field, electric potential energy. It is just like blah, blah, blah. And it is going to be even more confusing as we advance. The only way to avoid confusion and actually even enjoy to some extent the class is to read in advance. read the chapter in advance. So we're starting with chapter 18. And every week, we're going to cover the next chapter, one more chapter every week. Every 3 chapters, we're going to do a midterm here in class. And well, the midterm, I'm going to post a practice test. There will be no surprises. Exactly like before, if you stay awake in class, if you take the midterms, if you do the whole homework assignment, if you do the final, there is no way to fail. Now, everybody is going to have a chance to earn an A in the class, and I want everybody to try to do that. It is, if you invest the time required, there is no way you not to do well at the end of the semester, grade-wise. I received some emails last semester from people that didn't finish the semester with the grade that they expected. So if you think that you ended the previous semester with a grade lower than you should have received, please come and talk with me today or anytime this week. Okay, so now let's quickly go over the syllabus. We're doing the rest of the book starting from chapter 18. We're going to skip one chapter. The chapter on special relativity we're going to skip because it is not material relevant to any applications that you can encounter, and you're just going to, and also the coverage in the textbook is less than perfect. If we have time at the end of the semester, I'm going to talk about special relativity, but I'm not going to give any exam questions or anything related with relativity. So the rest of the material is interesting, at least from my point of view. Look, I used to say that everybody has to like physics, but I understand that this is not the case. And I understand that this is a course that is required for your major. And of course, there is going to be a lot of resentment because somebody is telling you what to do practically. I understand that. Please try to overcome those feelings. Try to benefit from this class. I can guarantee you that if you spend the time to understand what is going on, you're going to not only benefit professionally, but you're going to feel better when you're walking on the street and looking at the world around you. Because electricity, magnetism, optics, this is the entire modern world. Okay, so for people that haven't had the class before, let me see. I posted the syllabus on WebAssign, but in order you to see it, you have to register for WebAssign. And in order to register, you just go to webassign.net, I think. Let me see. Where is the link? Okay, webassign.net, and follow the links there. What you're going to need in order to register for this particular class is the class key. And the class key for this class is the following set of letters and numbers. Here is the class key, lowercase ISU, followed by the following numbers. So ISU, after that you have 0299, 0299, 2765, 2765. So please go and register as soon as possible. The cost is $91 for the semester, and they give you a grace period of something like 1 or 2 weeks, during which you can use the system without paying. So together with this $91 or $92, you get an access to e-version of the textbook, and the homework assignments are all posted on the system. They are automatically graded. The first 2 homework assignments are posted. You can start working on them as soon as you feel like. The deadline for the first assignment is this week, Friday, midnight. Exactly like before, you have, for every problem, you have 10 shots. So this means that you can try 10 times before the system decides that you cannot do the problem. In case if you encounter this situation, you try 10 times and you don't get the problem right, well, before getting to that point, it is better you to stop and either talk with me or talk with the tutors in room 104, or send me an email, and we're going to work on this test, on this problem together. Exactly like before, I'll try to solve at least 2 problems of your choice from homework assignment or from any other source. Exactly like before, you have the option to offer problems, good, interesting problems for midterms or for the final. But you have to do it well in advance so that we to solve the problem in class and everybody to agree that this is interesting problem and it is worth seeing that problem in a midterm test or the final. We're going to start weekly optional problem solving meetings, probably starting after the week after next week, because we have to arrange the schedule appropriately. I'll let you know when is the best time for me, and you're going to be invited. I'm also going to make recordings, and hopefully there will be no problem that is going to be left without solution. Let's see, questions, any questions, requests, comments? We're going to have again brownie points. So again, in a week or so, when I have the final class list, I'm going to post a Google Doc. Everybody's going to have access to it, and people are going to assign brownie points, and exactly like the first semester, those brownie points at the end of semesters are going to be counted as extra credit. And brownie points are assigned for every, just for paying attention in class, asking questions, making comments, or just smiling nicely also counts as a credit for brownie points. Okay. Questions, remarks? So we have something like 9 people that are signed for this class online. And unfortunately, for the moment, we still don't have a teaching assistant to handle Zoom questions and Zoom interaction, but hopefully this is going to be resolved by next time, or maybe next week, we'll see. It is a matter of resources. Well, if you don't have questions, let's start with the first section, chapter 18, that introduces the concept of electric charge, electric field, Gauss's law, Coulomb's law, basic concepts. So, well, the experiment shows, yes.
Sorry, I have a question. Last semester, I found that when I read the entirety of the textbook, I would sometimes just get lost, finding myself not always needing all the information. Do you have like a suggestion on how to best study the textbook before class to better prepare?
How to prepare, how to read the textbook before class. So look, the 10th edition of the textbook has many more diagrams and tables and all kinds of pictures and things. And it gives an impression that is huge amount of material in the chapter itself. And people, including myself, may get lost of what is important and what is not important. The way to handle this situation is to read in advance the chapter like you are reading a novel, maybe, the first reading. So this is not studying, this is just what is in this chapter. So if you're a fast reader, you can go over the chapter in about 30, 40 minutes, I guess. Different chapters have different lengths. If you're more ambitious, you can spend hours on a chapter. But even a quick read of the chapter should generate questions. And of course, when you are reading, the question is clear in your mind. The question could be something like, this statement contradicts to another statement, or it contradicts to common sense. At the moment when you encounter the situation, write it down. Write down the question because it is guaranteed that you're going to forget it. Write down that question and bring it here in class. At the moment when there is a question formulated in your mind, this means that you're 90% through learning this material. The problem is that when you cannot formulate the question, this is the difficult part. So again, everybody has different methods of studying. So what worked for me, more than 30 years ago, 40 years ago, doesn't work for you. 40 years ago, we didn't have the internet. In many courses, we didn't have a textbook. So we had to write down lecture notes and study from those lecture notes. Very different situation than the situation. You're exactly actually in opposite situations. There is so much information from so many sources that you don't know where to start. I would start with quick read of the material from the textbook. And here in class, I'm covering the important points. Well, what is important and what is not important sometimes is a matter of personal judgment. But if you feel like I haven't covered some topic that you feel that it has to be covered, maybe I just forgot. Just let me know and we're going to talk about it and we're going to cover it. Again, look, physics, like any other science, is a set of very simple things. The problem is that there are many of those simple things on top of each other. And if you miss one of those simple ingredients, the rest of the building falls apart. This is the problem in any science, actually, and math also. So let's try to stay on top of the material. And again, what is the best way to study is up to you. Different people have different approaches, and most of you have had quite a few college courses so far, and you already have your habits and your preferences. So follow them, and when you see that something that I do in class doesn't work, let me know. Privately, publicly, anonymously, and I'll try to accommodate you. Okay, questions again? Don't be shy. Don't forget that any question, any comment is rewarded with brownie points, and those brownie points actually benefit not only you, but benefit your classmates, because I'm sure that whatever question somebody has, the same question is in the mind of many other people in the class. Okay, so yes.
So if you struggled last semester, like for me, I was struggling pretty hard last semester. In order to just make sure that I'm feeling as confident as I can, since we're jumping right back into things, any suggestions other than just going back and reviewing the concepts? Anything that you think would be helpful?
So how to prevent losing track of what is going on in class. This is one way I would. Well, again, the only way is to read in advance. And look, the first semester probably was difficult for many people, but how many hours did you spend on average out of class?
A week,
Per week, yes.
probably 10 to 15.
Really?
Yeah.
Wow. So with 15 hours per week on average out of class work on the material, you should be able to finish the semester with an A or A minus. So I don't know how you finish the semester, but I would be very surprised if anybody spends 15 hours and gets less than A minus. So we can talk with you after class privately.
Okay.
But it is a matter of time. So again, when you're studying, if during those 15 hours you have the TV on and Facebook chat going on and other things, this is not real 15 hours. 15 hours would be just you and the textbook, right? This is how it works. Many people think that they can multitask, but the studies suggest that a person that is normal person with no mental distortions can handle one task at a time, not more than one task at a time. So 15 hours is a lot. If you do 15 hours, you should get an A. If you don't, come and talk with me, and we're going to make you a physics major eventually. Okay, other remarks and questions? when you are working on a homework problem, try it 2 or 3 times. If it doesn't come up right, stop. Don't waste time. Bring it here in class, bring it to me, talk with tutors. This is going to save time. Okay, other questions? If not, let's start with this chapter 18. So the experiment shows that under certain conditions, materials acquire some weird properties that we call electric charge, electric field, electric potential. And probably the simplest demonstration how it happens is take this plastic stick right here. Here's the plastic stick, a piece of fabric, and I chose them arbitrarily. If you rub them together, and after that, take this plastic stick, let's say, close to this simple device that we call electroscope. When you approach the electroscope with the plastic stick, you see that the aluminum leaves of this electroscope react. So here it is. Even without touching the electroscope feels the presence of this electrically charged stick. If you touch it, the electroscope reacts even better. And of course, you can discharge it. So how to explain those phenomena? The interaction between the electroscope and the stick from a distance, or the reaction of the electroscope of touching. So in order to explain those simple demonstrations, we have to accept that a concept that we call electric charge exists. So ordinary materials, like the material in this plastic stick, contain equal number of positive and negative electric charges. So we assume that there are 2 types of electric charges, positive and negative, and ordinary material like this plastic contains equal number of positive and negative. The result is electrically neutral material. When I rub this plastic stick with the fabric, some of the, let's say, negatively charged particles present in the plastic move and get in the fabric. As a result, there is a shortage of negatively charged particles on the plastic, and therefore a net positive electric charge on the plastic. In a similar manner, excess negative electric charges on the fabric, and therefore net negative electric charge on the fabric. So this is one interpretation of what is going on in the process of rubbing. Now, of course, we know that materials are made of atoms, and atoms contain electrons and positrons. The electrons carry electric charge that we call negative. Protons carry positive electric charge. Ordinary matter contains equal number of electrons and protons. When I rub them, some of the electrons that are in the plastic move and get stuck to the fabric. The result is positively charged plastic, negatively charged fabric. So this is one way to interpret and to make sense of what is going on in this process of rubbing. Now, we said that we have two types of electric charges, positive and negative. In other interpretations, you can think that there is only one electric charge, and it's anti-charge. So one charge and one anti-charge is one way to think about electric charges. Is it possible to invent a universe in which you have more than one charge and it's anti-charge? So this is a question that we are eventually going to discuss at the end of semester when we talk about modern physics. One interesting and non-trivial and property that we don't have a good explanation is that all charges, electric charges, are quantized. This means that all electric charges appear in portions. The smallest possible portion of electric charge is called elementary electric charge, and the elementary electric charge is denoted with the lowercase letter e, and it has electric charge, it carries electric charge equal to 1.6 times 10 to the negative 19 coulombs. So you're going to see later on that the SI unit for electric charge is a coulomb. A coulomb is not one of the 7 basic units in SI systems. We define a coulomb using the concept of electric current, unit for electric current, and we're going to define a coulomb later on when we talk about electric currents. So this is the smallest possible electric charge. You cannot get a fraction of this. Or maybe you can. We're going to talk about quarks and fractional electric charges at the end of semester, again, when we're talking about modern physics. But this is what the experiment shows. No electric charge exists that is smaller than one elementary electric charge. The electric charge, the total electric charge on this plastic rod, on this plastic stick, is going to be integer number of electric charges, elementary electric charges. In other words, the total charge Q on the stick or anywhere else is going to be integer number n times the elementary electric charge. Here, the integer number n is either 0 or 1, plus minus 1, or plus minus 2, or any other integer number. So why don't we have half elementary electric charge or 1/10 of elementary electric charge? We don't know. If you think about it, it is really non-trivial. Nature wants to tell us something, but what exactly does it tell us? We still don't understand completely. The electric charge is conserved. What does this mean? This means that imagine that this room is completely isolated from the external world. If you have certain amount of electric charge inside this room, that amount of electric charge stays unchanged while this room is closed. The change of the charge that is in this room is only due to charges that leave or come from outside. So this is one of the conservation laws that is absolutely firm conservation law. If you remember from the first semester, we encountered the following conservation laws. Conservation of energy. When you total energy, meaning energy that is kinetic plus gravitational potential plus elastic potential plus whatever. Energy is a number that is conserved for a system that is isolated from the external world. This conservation of energy is a result of a symmetry of nature. And the symmetry that conservation of energy is responsible for is the equivalency of different moments of time. So the uniformity of time results in conservation of energy and vice versa. A second conservation law that we encountered the first semester was conservation of linear momentum. And again, it corresponds to a symmetry of space. Different directions of space are equivalent to each other. The third conservation law that we encountered was conservation of angular momentum. If something is in a state of rotation, that state of rotation should be conserved if the system is isolated from the external world. Again, conservation of angular momentum corresponds to appropriate symmetry. And now this is the last conservation law, conservation of energy, that we are aware of. So keep in mind that practically the entire knowledge that we have, not only in physics, but in all other sciences, rests on those four basic conservation laws. And specifically now, conservation of electric charge is what we're talking about. Let me see. Any remarks so far? And questions? Yes.
What is the Q again?
Q is total electric charge. So standard notation for electric charge, amount of electric charge, is either lower case letter Q or sometimes uppercase letter Q. Yes.
And what's the symmetry that leads to conservation of electricity?
What is the symmetry corresponding to conservation of electric charge? Well, the corresponding symmetry is quantum mechanical symmetry that lives, at least the way we understand it now, that lives in Hilbert space. So the corresponding symmetry is a symmetry of the change of the phase of the wave function. This is the way we understand and interpret it now. But that's actually a very, very interesting and deep question, actually. Yes.
So is that having to do with the whole experiments about whether a photon is a particle or a wave? Or is that
so how is this related with particle wave duality? Well, everything is related. And again, we look, since you're spending 15 hours per week on physics, you better take a second major or minor in physics, and we're going to discuss those questions in more detail in quantum mechanics classes. So at the end of the semester, we're going to talk about particle wave duality. And what I'm going to say at that time is going to be different from what is in the textbook. Yes.
Somebody else was question on the things like quantum fluctuation.
Quantum fluctuation. Well, we're going to talk again very conceptually on the topic of Heisenberg uncertainty principle and quantum fluctuations, and those are topics that are again going to be discussed more conversationally rather than quantitatively. And again, keep in mind that you can very easily, if you're taking calculus, you can very easily sign up for a minor in physics and get a minor with very few extra classes. And questions of that type we're going to discuss in appropriate physics classes. Well, still, this is introductory class, and we have certain topics that we have to cover, and actually the topics related with modern physics have to be covered in completely separate class, and they used to be covered in a separate class, but now we changed the things. So whatever used to be covered in many semesters, now we're covering it in 2 semesters, but in much less detail than we should. Okay, let's see other questions and remarks. So again, those are very interesting questions. If you are interested in philosophy, if you want to understand how the things work, one way to get certain level of understanding is to study physics. That's it. Okay, so charge is conserved. The next property of electric charges is that you can observe that like charges repel. In other words, plus and plus repel, minus and minus repel, while plus and minus attract. And you can see how it works by looking at the electroscope, the standard electroscope. Here I'm charging the stick with positive electric charge. I'm touching the electroscope, and some of the excess positive charge or shortage of negative charge is going to be transferred to the metal part of the electroscope. Now the electroscope is positively charged, and look what happens. Here is the body of the electroscope. So it has this metal sphere on top, and after that it is connected with a metal wire to those 2 aluminum leaves. So when I charge this electroscope positively, let's say, or negatively, it doesn't matter. One property of metals is that those positive charges are going to be distributed through the entire body of the metal. Well, through the surface, strictly speaking. But some of the positive charges are going to be to end at the 2 aluminum leaves. And now, since like charges repel, those 2 aluminum leaves are going to feel repulsive forces, and they are going to separate. And here it is, a demonstration that like charges repel. The same thing would happen if you charge the electroscope with negative electric charge. Now, instead of rubbing like this, we have a little bit higher tech rubbing system. On this device that is called Van der Graaf generator, you have a rubber belt that is going to be rubbing against some brushes that are inside. And the result of this rubbing is going to be that the rubber belt is going to acquire electric charge, let's say positive electric charge. That positive electric charge is going to be transferred on the metal sphere of this electroscope. And I'm going to have positively charged, let's say, metal sphere. And here, let's do it. It is rubbing it by turning it. Oh, what happened? It's turned it off. Oops, yeah. So it doesn't work if it is not connected to the grid, but we can always connect it like this. Okay. Okay, so you have a small electric charge that is constantly being moved to the metal sphere that you see right here. People that are online probably cannot see it, but next time I promise to have assistant here to work with the camera. So you're going to see that electric charges that are generated eventually leave on the surface of the metal. In this case, on the surface of this metal sphere. If I turn off the generator, this metal sphere is still electrically charged. And I can feel the presence of electric charges just by getting the electroscope close to the charge. If I touch it, I'm going to charge the electroscope completely. If I don't touch it, the electroscope feels the electric field around the charged metal sphere. And actually, with a little bit of experience, I can transfer electric charge from the charged object to the electroscope without direct contact. And I'm going to show you how to do it. For the moment, here it is, and touching it, here it is. The electroscope is completely charged. I can discharge it by this second metal sphere is connected to the ground, and by touching the electroscope, the excess charges are going to fall in the ground, and the electroscope is eventually going to be completely discharged. I need a good contact in order to do it, and I need to have connection to the ground. Here it is. It completely discharged itself. So this metal sphere is connected to the ground, and objects that are connected to the ground are electrically neutral. And don't look at this connection. It doesn't exist. It's just connecting it to the ground. Now, how to transfer charge from this metal sphere into the electroscope without direct contact. We're going to discuss how to do it next time. And next time, so on Wednesday, we're going to talk about Coulomb's law, Gauss's law, and charging by induction. And please register for WebAssign as soon as possible. The first homework assignment is due on Friday. And if you haven't received an email from me with instructions for connection to WebAssign, please send me an email so I to add your name and your email to the list, to the class list. See you on Wednesday. Okay, students, next time I'll try to have a teaching assistant to work with the camera and to handle questions that are online. For the moment, I'm alone in the classroom. Next time, it is going to be better managed. So see you on Wednesday.